On this lecture, we're going to dive into details of assembly language. I gave some examples in the last class, and I walked back and forth between C code and how it's broken up into assembly language. And there were some very simple mnemonics and operations that were gone over there. In this class, we're actually going to go into the instruction level, into the instruction level of the code, and we will, I'll discuss what's there, how those things are constructed, and also, hopefully, we'll still have time at the end of class for me to dive into actually applying it to some sort of, applying it to building some sort of detection or analysis signatures for it. So, so I introduced general assembly language, a handful of the compiler, specifics that you'll need to know when you're trying to understand code. In this lecture, I'm going to dive into specifically the Intel or AMD instruction set. So both of them use the same instruction set, whether you get an Intel processor or an AMD processor. They do have a handful of different features, and those will be illustrated in a lot of the documentation. But for the most part, they have a compatible architecture. And the reason for that is so that they can sell hardware that'll run any program that you download off the internet without any modifications. So you don't have to sell two different versions of the program. That's different for like I've got my work iPhone and this other phone that runs Android. Those are two operating systems, and I think these two may even be running on two different CPUs. I'm not entirely certain. But because of that, a lot of times application developers that want to upload stuff to the application store for each one of these platforms actually need to compile it and even write two different versions of it. So people who write games, people who write Windows operating systems, stuff like that, they don't want to have to write two versions of it for each of these things. So that's the reason why all your systems today are based on this architecture that we're going to go over. That includes the Macs that some of you have. That's a relatively new development since 2005. Apple used to use a different CPU and had the problem of a lack of adoption based upon that anybody who was wanting to write an application that would run on a Mac versus would run on my PC system here had to get a different compiler for the Mac.
What CPU did they used to use?
They used to use the PowerPC one, which is kind of a partnership between, I believe it was Motorola at the time, which is now called Freescale. That part of it is anyways, and IBM. So IBM still uses it for a lot of their high-end CPU processing applications. So some of you who are working in the distributed computing space, say working with Dr. Wilsey or someone, you might actually hear about it. I don't actually know if we have any of those, but they're generally used for a lot of the higher-end processing work. So Apple used a version of it called PowerPC for a long time. And that was just I would say, trimmed down version of what's common in those mainframes. So if you go and do research on different architectures, so as I said, the phone, like this one that's from Apple, has a ARM processor in it, and I believe the one that's in this phone is actually designed by Apple. It's either by Apple or I think Samsung maybe, I can't remember, it's one of the two. And that has a completely different 64-bit instruction set than my system. It also has some other different characteristics to it as well. There's also another common one that's called MIPS, and like I mentioned, power and all that. The reason I'm kind of mentioning all these is if you do some research on those architectures, you'll be able to go through here and actually list what possibly might be a different list of say specific features and stuff about those. In our case, the Intel x86 64-bit instruction set It's a register memory architecture, and we talked about that briefly, what that means last class. Just to kind of summarize, it means that when I want to do an operation like a mathematical operation, like an addition or subtraction or something like that, this processor actually lets me operate on values that are stored in memory directly, as well as ones that are stored in local registers. This is different from a load store architecture where you need to bring everything into the register or everything into the CPU registers, and then all operations only work on the local CPU register memory. Additionally, it has some purpose-specific registers, which means that certain operations will be pinned to using certain registers for certain aspects of whatever operation it is they're trying to get done. And we'll talk more about that later on when I start to talk about the different registers that are in the instruction set. Originally, x86, so going all the way back to the Intel 8086, it offered 8 registers. The most recent ones, 32-bit registers. I actually separate these out. 32-bit mode offers you 32 registers to use, so that's basically, 32-bit mode offers you 8 registers to use, so that's kind of 8 local variables, local memory, if you want to think about it that way. And then 64-bit mode extends this by adding another 8, so it extends it to 16, which is actually in line with a lot more 64-bit processors. These are called general purpose registers, which means that you can generally operate on each one of them, or I should say they are interchangeable with each other in any operation that'll work with register data. Some of them, again, have some specific purpose to them, but you can also generally use them. There are a handful of registers that I really won't go into that you don't get direct access to, but you do get to see the information from them. We'll probably talk about that next week, and that specifically relates to how, a great example of that specifically relates to how jumping branching conditions are made. It has these section selector registers set that I'm not really going to go into. You typically don't use those in a lot of standard programs. Those are typically used for dealing with system level stuff. It offers direct and indirect memory access modes, and this basically means that you can access memory either directly by address, or if you want to, you can access memory indirectly by, say, providing a variable as your memory address, or a register as your memory address. And then it also provides, or I should say, offers variable length instructions. This one is probably one of the most, or I should say, one of the more complicating factors of it, in that your instructions can actually be different sizes depending on which one it is. This does reduce the amount of predictability there is, and it also makes it a lot more difficult for you to chop up your program into a list of instructions. So we'll also talk through approaches to dealing with that problem as well. In addition to these, it also has internal flags, instruction pointer, which is whatever your current execution point is. So all your instructions are a sequence of bytes that live in memory somewhere. The instruction pointer is a register that keeps track of where that where is. And then machine registers, which is just another set of registers that are used for various, typically system level interaction or system level features. So another thing you'll run into is what I call assembly language source variations. All instructions, really, so all the instructions you're seeing written in assembly language, they're really just binary data in memory or on disk. So the actual human readable code that you see is never ever seen by the processor. and never seen really by parts of the processor except for what's called the assembler that really just does a one-to-one translation of that text into the binary form or back. So you can do a very easy two-way kind of translation between those two. Because of this, you're going to probably encounter different tools and different people's own point of view or opinion as to how this binary code should be represented. The one that I've been using a lot in class up to this point has been what's called the AT&T or UNIX syntax or GNU syntax. That's the one that basically writes the operations in this format, which is the operation name comes first, and it comes first in both forms. Then it's the source and then the destination. So the way I like to think about it is if I'm reading what's going to happen from right or from left to right, you have the operation. And I'll do it in you guys' way. So you have the operation first, which tells you what you're going to do. You have the you have the source, which is where it tells you where to get the data from. And there could be more than one source. And then it has the destination, which is where you want the result of some operation to end up. So where you want a sum from an addition to end up, that type of thing. So the way I kind of think about it is in the AT&T syntax, between the operation arguments, the operands, I basically have a right-hand pointing arrow from the source to the destination. Also, you'll frequently see this. It's not all the time, but it happens sometimes, and it usually happens in a lot of the Linux assemblers. Is you'll see the registers are actually prefixed with a little % symbol, so they have what they call a sigil. They'll use that to denote that something's supposed to be a register instead of a memory location. Most of the time, AT&T, Unix, GNU syntax, if you don't have that and you just have plain text, then it's going to look like in this case, if I didn't have that % sign, rather than it knowing that I'm trying to talk about a register in that position, it's going to think that I'm actually talking about a memory location that has a label assigned to it or a variable name that's RAX. So it gives you the ability to actually have variables with those names and then uses variable labels as memory locations. So it basically makes the assembler's job easier if you can put these little, or I should say, if they force the language to put these little things in front of everything that's going to be a register. Yeah.
How do you create a label, right? So you can jump to a static address, right?
Yes.
Jump to a static address.
Yep.
If you want to create a label, do you create that in assembly, or
yeah. Yep.
Try to look at the syntax.
And so I can show you the syntax. That's another thing that varies. And when we jump into the code that I was working on in the last class, I can show you some labels in there. Generally speaking, the label is actually just something that you'll put, that you, the author, can put in your code anywhere. When the assembler runs, it actually finds out what memory position that label has been placed at, and it will convert all iterations of that label that are in the system into the memory address, the numeric address. It basically just does a find and replace on all of them. Yeah, functions like that, but you won't. That's not the construct that you'll use. Yeah. But yeah, the idea is it does exactly the same thing as the. So it works kind of like the pound define does in C, and that being like a C preprocessor thing. That one does a very simple find and replace. It's the same thing, except it's very application specific for labels. So Intel or Microsoft syntax, you'll find that a lot of the tools that you use that were originally written for Windows or that work in Windows will use this syntax. And this is kind of why I'm saying you're going to run across both of these, is that when we do anything in Linux, a lot of times you'll end up looking at stuff that's using this syntax. When you're in Windows and using Windows tools or using like Visual Studio's debugger and stuff like that, you're going to see it using this syntax instead. And this syntax Really, the key thing to remember here is that they swap the destination and the source. So in this case, they're writing it in the order that you would expect something to be written if you were writing the operation in C. So like x equals, or x plus equals y, or x minus equals y, that type of thing. Y is unchanged, but x is changed in that operation. And x happens to be the thing that's on the left-hand side. So the way Microsoft and Intel decided to use it was they put the destination on the left-hand side. So I think about it as operation, destination, and then left arrow from the source. So it's going the other way, or you can put an equal sign too. So the Intel Microsoft syntax, that works, or I should say that reads very similarly to how you'd be writing the operation in C, which is the result of whatever operation you want to run is stored in whatever happens to be the leftmost element, whether it's a register or memory location or something like that. As an example, I actually wrote the same operation. And apologies, this should have been a mov Q, not a mov L. I'll make sure that I fix that. But the concept stays the same. Is that in this, oops, come on. There we go. In this case, you'll take whatever was contained in RAX, and then you'll make a copy of it and put that copy into RBX, overwriting anything that was in RBX, which is the name of your register. And then in this case, same thing's the case. It just happens to be that the operations are reversed. Why is it like this? I don't know. If I were to guess, the AT&T UNIX syntax, like that predates probably the Intel syntax by some amount of time. Was an attempt at some point to standardize across the different architectures. So you'll see that systems that use it, they tend to have a lot more consistency across different CPU lines than systems that are using this syntax. So as the name would suggest, this is the syntax that Intel was popularizing using in their technical documentation. And then this was the one that AT&T commonly used in their Unix operating system, and that which was those which came out of like UC Berkeley's computing systems lab and all that stuff. So it just happened to be basically two almost parallel evolutions that were based in different kind of language theories, I guess. So.
You need Bell Labs and AT&T?
Yep. Yeah. Yes, I mean, Unix, AT&T's Unix, that dates back to what, the 70s or whatever. So Intel's x86 and all that stuff is a lot more recent. Intel was actually a memory company for a long time before they took the risk on developing microcontrollers, microsystems. And so they sold a lot of smaller microcontrollers. Some of you have probably used the 8085, I think, in microsystem design. Probably have used a variant of it, or maybe not. I don't know. I know I did when I was here, and it has that's also an Intel architecture that's very popularly used and re-implemented all over the place. All the tech docs look like this, but it has a syntax and set of operations that's very similar to x86, but it misses a lot, and it has a lot of extra operations that are very specific to the microcontrollers. So because Intel was in that game for this, they just stuck with it. Microsoft, of course, adopted this for their assembler because of their tie to the Intel platform back in the day. So on the subject of instruction lengths, remember earlier I mentioned that the x86 instructions, they're a sequence of bytes. So they're a sequence of bytes that describe a unique atomic CPU operation. I said it was variable width. which means there's no fixed size for all instructions. So there's no like definition that says an instruction is 10 bytes long or something like that. There are CPU architectures that do work that way. There was actually one that Intel does sell and did sell as a cooperative with HP for a long time that actually had very fixed word instructions. This one doesn't have that, which means I can't just go and break up my program every like 32 bytes or every 10 bytes or something. I actually have to, or I should say the assembler actually has to look at whatever the first byte is in the program, and then from that decide whether it's a 2 byte or a 10 byte or a 4 byte or a 1 byte instruction based upon what that thing's value is. So I've got some examples here, and you can kind of see here like how little or much sense a lot of this makes. I will say that most of the time what they attempt to do, from what I've seen, is the instructions that are most likely to be used or most frequently used in most programs are the shorter ones, and the ones that are least likely to be used are the longer ones. So for instance, this operation, which allows you to jump to an address that's provided inside of the RAX register, that instruction is only 2 bytes long, because you'll do a lot of jumping in your code. You'll write a lot of go-tos, or your compiler will introduce a lot of go-tos based upon your branching logic. However, moving an extremely large value, which is an immediate, and this is another example of these little what they call sigils, which are basically the value following this little symbol is designed to be of a, or is specified to be of a certain type based upon what the little symbol is. This one's a $, which means that any of the data following the $sign is supposed to be a literal number. In this language, if I don't have that, then the assembler interprets this number to be an address instead of a number, instead of a value. So I put the $sign in front of it, and then it interprets it as a number, and it stores the number, which is basically 8 zeros followed by 8 ones, into the RBX register. If I didn't do that, then what it would do, if I remember correctly, is it would go into memory and it would try and find out what 8 bytes are at that memory location, take those 8 bytes out of memory, and put them into the RBX register. So that's the difference that a single $sign could make. That second case, the memory load and store, I don't know how many bytes that is, but I can tell you that this one, where you're moving the numeric value, and I actually just truncated the numeric value to fit space in the slide here, but this, if any of you want to do the math, feel free, is the same as this. Stores that value into RBX. That's actually 10 bytes of code. And we'll get into why that is, but some of you want to jump ahead. You can think of how many bytes this is, and then subtract that from the total to find out what the instruction size is. The next one is a super complicated one, but it's actually commonly used, or I should say it's it may be more commonly used than this, and that is adding an immediate value. What they call an immediate value is just a name for a numeric value. So add the hexadecimal value 1, 2 into the memory location that's 8 bytes less than whatever EBP happens to contain. So EBP is a register, contains a number. I want EBP, or I want my CPU to go and find the memory location that EBP has, and then walk back 8 bytes from there, and then I want it to add 12 to whatever value is already in there, which means it's got to pull the value out of there, it's got to add 12 to it, and then it's got to write that back to the destination. And this is a really good example of the source destination concept that they use in all the x86 instructions, which is that This one basically ends up being, 1, 2 plus x, or I should say x equals 1, 2 plus x is what the operation that's being done here is for the most part. So this one was actually pulled from one of those operations I had in the code that we compiled in the last class. So some of you might recognize it from that too. So, and then this is just me explaining that, but you'll notice this one's only 4 bytes long, and that's because this is a really common one that's used a lot. You end up adding some random value to a variable very frequently, and that's what this is this is x equals 12 plus x, or hex 12 plus x. So x equals 18 plus x, really. But that ends up being 4 bytes. And that ends up being a lot more consistent. You can actually go through and do a statistical analysis of all the instructions that x86 offers and find out on average how many bytes are, how many bytes per operation are common. One of the reasons why they try and assign the smaller instructions, keep it condensed, keep it compacted, to the more frequently used instructions is because they want to try and drive that number down when they're architecting these CPUs. They want to make sure that they can fit the most number of operations in the smallest amount of memory.
I asked a question you answered last week. You just tell me to watch the video. But
That's fine.
if you were to do like a hex dump of a file or whatever, and you knew based on maybe some header information what instruction set it was using,
Yeah.
you translate the hex instructions back to the
Yeah. So I can I'm gonna do this.
like with I did some microcontroller work at my co-op, and I remember having to like look at the instruction set they had and kind of work backwards with some things to know what like a no-op was in hex.
So I've got this ASM program, right? So this is the program that we were looking at from last week. And here's one of the add instructions, and then here's another one. So what I ended up doing for the sake of the example I just showed you in the slide was I actually changed the immediate value here. But this is basically, this one basically gets a variable that's temporarily stored on the heap. So temporarily stored in scope local memory. And then it adds 1 to it and then stores that sum back into the register. So it's from here to there. So after I've compiled this, so I can compile this thing, and if you don't know, you can do. I'm going to do this also. Oh wait, I don't have to do that. So so you can compile stuff into an object file like this, just like with a C program. So I can compile the disassembly that I have. So if I wanted to, I can go back and edit that. So for instance, whoops, I'm going to go to that add again, right? So I can go and put our instruction there, or I should say our modification there. And then what you can do is you can do this. Objdump is basically the tool that allows you to dump the binary contents within a program file for the most part. It was originally written for dealing with like Unix programs and everything, Linux programs. It actually will work if you install the right libraries on dumping Windows contents as well. I'll go and do this for a second so you can see the different features and get an idea of what I'm trying to do here. So what I was actually going to do was I can dump source code. I can also disassemble. So I can disassemble the contents of executable sections if I want. So my program is broken up into sections like I showed you before. Some of those sections have code, some of them have data. This tool will actually go through, and if the section contains code, it will try and disassemble that code so that you can view it. So I'm going to use this on the object file that I just created right here. So I'm just going to use the -s, which is actually a really nice one because if you're ever working on debugging a program that you've been working on, -S, in addition to doing disassembly, will actually show you some higher level source code if that's available too, and if your version of the tool supports it. So here's that again, and here's the modification that I made, right? And so what you'll see in the columns on the left-hand side, those are the literal bytes that are in the program. So for instance, this one right here, this addl, it's a 4-byte instruction, and if you look at all 4 of those bytes, you can probably guess which one represents the value 12 that I just put in there. So one of the bytes in here represents the 12, and then this represents, or I'll say part of this represents the instruction, and then these represent some other kind of instruction attributes. So the add instruction can operate many different ways and use different registers and everything like that. So for instance, you can gather that this right here, that I chose RBP instead of EAX, or instead of EDX, or instead of some other variable, or some other, like RDI, that I happen to choose this one, that's probably encoded in one of these 3 bytes somewhere. And also, the fact that I'm using the memory operation, so I'm dereferencing with the parentheses and also with this -8, that's also located in there somewhere. And so I'll tell you that -8, or 8 less than 0, is really, if you think about it in terms of unsigned values, is 0, 0 minus 8, which is going to be F8, which is actually right here. So I've just been able to pick out 2 of the data points that are in my source code, and then assign them to 2 different bytes that are in there, which means that all the rest of the information that describes this instruction, like that it's an add instruction, that it's working on 32-bit values because of the L, that it is working on this register, all that information is stored in this right here somewhere. So
it doesn't, it factors in a lot of that. It doesn't just have like a standard hex value for a move command. It's going to change based on what's...
Yep. Yeah, and actually if you want, we can do this. So I can look at all the move operations that are in here. And this is where it can get really interesting too, is every single one of those is a type of move operation. But the first byte on them, on one of them it's 48, and you have a 3-byte instruction up there. And then the one underneath that, you have a 7-byte instruction and it's C7. And then go down a little ways more, and then it's 8B and it's 3 bytes. And then 2 more lines under that. So we'll be here now, and it's 89, and it's 2 bytes. And it's all depending on what registers are part of this operation, what type of move it is, all that stuff. So
I don't want to get you too far off that question, but so the Python's being built to pull out the metadata from files or whatever.
Yep.
Is there similar tools to look at disassemble objects like this?
Yeah.
Pull out kind of like, oh, this looks like a move with these parameters or whatever.
Yep. Well, I mean, that's literally what this tool's doing right here. Is this tool's getting byte streams that are this. So if I was to, let me see, this one right here, right? So if I was to do this, so I literally have this file, and it's got an ELF header, which means it's an ELF type file. Then it's got some data in here. I don't exactly know what all that data is. Somewhere around here I have code. And if I want to try and search for it there, So this is probably one of them. So you can see this is one of those move instructions where it's going to be moving, I'm going to guess, the value 0 into a register.
Oh, one of the move L commands.
Yep. And then here's the other one that's moving the value 4 into another register. And you can see some of the other differences here are that this one's C745F8, this one's C745FC. And so the F8 and the FC, actually I think that those are the register indirects. So one of them is 4 offset, or -4 from the stack pointer, the other one's -8 from the stack pointer. So it's moving a 32-bit value into one spot, and then it's moving another one just on top of that in memory. And so this is literally what the CPU is seeing in memory here. And the objdump tool is taking this mess that's unreadable and turning it into something that you can read. There's another tool too. Let's see if I can install it, because I... Oh. Okay. Maybe I don't have... Huh, that's weird. Oh, I know what happened. Well, oh well. It's not going to come up. Just do that then. So, UC wireless, I don't know. I was having trouble on it earlier. So I can't but there's another tool I was going to load up here to show you. We'll get through the slides and then I'll jump back to that actually. But basically it was just going to be a different assembler that I could run across that same code, and you could see what it looks like in the other syntax. So I think that assembler is actually, you know what? No, I don't have it there either. I haven't installed any of that stuff. But I do have that one installed on the in Remnix. So yeah. So that's kind of what I'm talking about, the different instruction lengths. And I think the move example demonstration was a really good example of that, where the same instruction that you would see that's referenced by this MOV code that that's human readable to you, even that can define different instructions at different lengths. You can't even rely upon that all instructions that are moving data from one place to another are the same width. So generally, this is the diagram for your general instruction formats. So they can be anywhere from 1 byte to 15 bytes, depending upon their purpose. And so I think 15 bytes or 16 bytes was the longest. Apologies for that weird tilde. I guess typesetter puts tilde on top of the 1 if I do that. x86 attempts to reserve the shorter instructions for the more frequent operations. So common layout is below. It's really built out of these, your instruction, or what operation you want to do and how you want to do it is really defined in these three. And then following that are the arguments. Generally speaking, you end up having a displacement argument and then an immediate argument. So if you remember on some of those examples that we had, you had a displacement that was like -8 and showed up as F8, and that was like the first argument after the 2 bytes that were the instruction on the 4 byte or the 7 byte instructions. And then the immediate value or the immediate address or something like that is typically what follows that to describe, say, where you want to get data from or what data you want to use. So for instance, when we were adding 12 to something, even though the instruction was written, we'll jump up here, even though this instruction is written, add 12 into this, or add 12 to the value at this memory location and then store it in that memory location, 12 ended up being the last value that was in the instruction, ended up being at the end of the instruction. And then all of this mess here was actually described further up in the middle of the instruction and near the front of it. That's also one of the reasons why Intel uses the syntax they do, where they put this destination first, where it's going to go first, is because that kind of seems to be where it is located in the instruction as well. But generally speaking, this is the organization of the bytes. The nice thing, or the painful thing, depending on your point of view, for the Intel architecture is that any of these fields, except for the operation, of course, but any of these fields can be eliminated if it's not necessary for that instruction. So from their perspective, that helps with compactness. It means that the processor reads basically 1 or 2 bytes or up to 4 bytes. I won't go into detail on those, but for the most part, there's an operation that's 1 or 2 bytes, and those operations can have an extra 1 or 2 bytes to describe a modified version of them. It'll read those 2 first, and then that gives it all the information it needs to know so that it can go and read 1 more byte or 10 more bytes out of memory or something like that. This mod register memory field typically tells it, in addition to the operation itself, so a combination of some of the data that's in here and some of the data that's in here is what tells it what registers to use in the different arguments, and also possibly where to store the information. So all that is like compressed into this. This scaling byte helps for stores the information for a scaled address operation. So if you're going to do an operation where you want to find a memory address that is like x times 4 plus 10, this thing stores part of that information. That's what's called scaling. And then displacement, immediate, these are where your actual arguments are. The things that you're going to be reading out of the source code as arguments when you're looking at assembly listing, that's what the displacement, immediate, and I just kind of put this ... here because there's some edge cases where there's a third argument. So CPU registers, I was mentioning earlier that the way x86 works, and this attempts to go into explain why you have, why they're not just numbered, but they have these alphanumeric names to them, is because historically, Intel architecture, back when it was designed in the 70s and the 80s, actually had a number of registers that had a specific role within the instruction set. This isn't the case with all architectures. So you run into a lot like the Motorola 68K or 68,000, whatever you want to call it, architecture that doesn't work this way, or 6502 doesn't necessarily work this way. But we'll focus on this one. And more recently, they've been trying to move away from having that like role definition to them. So when they came out with the 64-bit architecture, they actually introduced numerical names to all of them. So R0 through R15. So you have 16 registers, R0 through R15. You can address them that way. But also the classic names, which have these different roles, are also used. And the reason why they have these different roles is there are a handful of instructions where the value of that register, of that specific register and none other, is used for a particular purpose. So in this case, the RAX, there are a handful of instructions, and also historically there's a handful of operating system functions where RAX was used as the place to store results. So all operations, the result would frequently be written into RAX. And that way, on older systems where they were trying to be more, they were trying to conserve memory usage, and conserve time, you could actually have instructions that would have a single byte that would do something with a defined set of registers as the input and then RAX as the output. RCX, which is R1, it's also important to note here too that the alphanumeric registers aren't listed in alphanumeric order. So there is a index ordering to them that's numeric, but it doesn't follow the normal alphanumeric convention, or I should say alphabetic convention on ordering. So register 1, or the second register, is your counter. There are a number of instructions that will work more efficiently if the value being stored, if say I in a for loop or I in a while loop or something like that, just to use a standard convention, I or j, if your iterating variable in a counter loop is stored in the RCX register. So a really common convention you're going to encounter is cases where entering a loop that's going to run through a number of iterations, that value, if it's numeric, may be placed into this variable first, and then this variable actually has a number of instructions, one of which is actually called loop, that it tests for. Or I should say that's hard-coded to test for this particular register. Another one, RDX, is your data register, frequently used as an additional argument in some operations, and some instructions just assume that RDX and RAX are two parts of a three-way operation where the result is overwritten in RAX. So it's called the general purpose data register. Base register frequently uses a base address or sometimes counter. This one is commonly used to point to, say, the first element in a data structure that you're dealing with. So if any of you have made a struct or a class in C++, a lot of times the base address of that, when you do a such and such equals new, my struct or new my class or something, that pointer is really pointing to the first element in your data structure. It's very common for convention to use this register to keep track of that pointer when you're trying to deal with like all of your class members. So if you have class member functions and stuff like that, you usually reference the this to be the current instance of my class, and that's always a this pointer. It's very common that the this pointer is really directly translating to RBX in a lot of those cases. So when you're analyzing code, and you'll see a lot of these memory operations that are running against this register, that may help inform you to be able to follow some of the C++ class code that's going on. RSP and RBP, those are used for setting the top and the base of your stack. The CPU actually has a large number of stack operations, such as pop and push, that operate using RSP, and then RBP is used to basically keep track of where that stack ends or where it started, depending upon the API. And then finally, there's two more registers that are typically used as pointer registers. That's RSI and RDI. There's a number of instructions that rely upon using both of these for doing array operations. So one example would be if you have one array and then you want to perform an XOR operation and on every single element of that array non-destructively, and you want to store the result in another array. There are a number of operations that are built into the instruction set that are hard-coded to basically iterate across that loop for you. So you can run the instruction multiple times, and it will take whatever data is in the RSI offset from some variable, perform an operation on it, and then store it in another spot in memory that's defined by RDI. So a really common loop that you'll see is, or I should say really common construct you'll see in assembly language is a very tight loop, so a very small number of instructions that's based around what they call a string instruction, So like a moveS or addS or XORS or whatever. I can't remember exactly what all operations it supports. As I said earlier, there's almost like 1,000 instructions in x86, so I can't keep track of them all. But basically, this allows you to support the cases where I want to move an array or a matrix from one spot to another. There's a lot of instructions that do that really quickly. Some of you who've taken the computer architecture courses and stuff might also be familiar with the vector instructions. Those aren't the ones I'm talking about. Those are newer introduced instructions that allow you to do, they're basically a more efficient way to do the same type of thing with a lot broader set of operations. So this is all the CPU registers that you're allowed to use, like, on dealing with data within the processor. And as I said, the 64-bit system introduces these extra 8 down here that you can also reference. What you saw up here earlier as well was some features that allow you to address memory. And I have that also documented right here on this slide. And this is, say, register addressing is one of the approaches that you can do. Basically, they have this concept of addressing modes. And the addressing modes is that if I have data stored in my system somewhere, whether it's in memory or whether it's in register or whether it's hard-coded into the instruction, I can reference that data in some manner. And those bytes in the instructions you saw earlier, how like the move instruction had a whole bunch of different bytes, that also informs which one of these addressing modes is going to be used, and then which, I should say, how to interpret the these things, the displacement and the immediate values and stuff like that. That's also provided in the instruction. It's actually getting close to the end of class, so I'll try and wrap this up, but I'll just say that one thing that's really interesting about this architecture and can add some complication when you're doing analysis of machine code is that they support features where you can take like one number in a register, multiply it by a second number, add that to a third number, and then add a fourth number to that, all in one big instruction like this. So, that said, like in this case, you're taking, I believe it's RBX, multiply it by 4, add RDX to it, and then add 8 to it, which looks like a hugely complicated thing. I included it up here because you'll run into it actually more often than you like. If you think about matrix operations and linear algebra, matrix methods, stuff like that that you may have had to do in the past, think of like data operations or encryption algorithms and things, stuff that has to deal with like n-way data manipulation. That's where a lot of these processors were written on attacking problems like that. And because they were written to attack problems like that, they have all of these instructions hard-coded into them to deal with data organized in many different dimensional arrays in memory and stuff like that. And because of that, they have a whole bunch of very efficient ways of accessing data that's organized in memory. So you'll run into these. It's probably useful to wrap your heads around kind of what's going on here, because that way they won't trip you up when you do encounter them when you're trying to like unwind an operation from a piece of malware or something. So that said, I'll go ahead and end class because I'm like 2 minutes over.